Yes, just 1 minute.
Yeah, sure.
There we go. Right, so good morning again. So last time we spoke about the automorphism group, the Miyamoto group, this special subgroup of automorphisms, which is naturally associated to the algebra. And we discussed about axes and when they were closed under the action of this Miyamoto group. And we discussed some properties of the axial algebra and whether they were stable under this natural change of axes, i.e. Two sets of axes are equivalent when their closures, that is under the Miyamoto group, when their closures are equal. And it turns out that this is the natural sort of equivalence class, equivalence relation on axes where things in the same equivalence class give us the same properties, or we like properties which the same equivalence class of axes preserve these properties. And we saw that the Miyamoto group and generation of the algebra were both examples where if we change the axes within this equivalence class, then we still have generation. We still have the same Miyamoto group. Okay, so today, we just finished last time I gave you the definition of a Frobenius form. So today I want to flesh that out a bit more, give you some results on the Frobenius form, and also move on to ideals and hopefully get maybe all of the way, but if not, a good proportion of the way through saying some things about ideals. Okay, so the Frobenius form. So as I was saying last time, this is a bilinear form, non-zero bilinear form defined on the algebra. And the property is that it associates with the algebra product. So that is that we can move, when we have b times c here, so the product b times c, we can move this across the comma in the bilinear form and instead do a times b, comma c. And this must hold for all elements in the algebra. And this is motivated by the fact that we see such a bilinear form in the Griess algebra, and also VOAs have a similar type concept. Okay, so what properties does this Frobenius form have? Well, the first thing to note is that a Frobenius form is necessarily symmetric. Oops, I missed out form. A Frobenius form is symmetric. So why is that? Well, just as a warm-up for today. So axial algebras are defined as being spanned by products of axes. So everything in an axial algebra can be written as the sum of products of axes. So in order to prove such a result on the Frobenius form, we just need to consider a basis. And let's take the basis of products. I mean, there are many more products maybe than there are needed to be in the basis, but if we prove it for all products, that suffices. Suffices to prove with or to prove for products of axes And so let V and W be products of axes. And I want to show that V comma W is equal to W comma V. That is, it's symmetric. Well, because let's say W is a product of axes, so we can write W is a product of axes. So let's just look at one of the brackets there, W1 times W2. So as we're at the beginning of the lecture and just warming up, let me just comment. So W here, I guess an aside, e.g. W could be something like A times B times C times A times D. I don't know, something like that. So there are lots of different products and brackets here. And when I pick W1 and W2, I don't get just free choice over these, but there must be some outer brackets here, right? So for instance, I can't pick W to be A times B times something to do with C because this bracket is in the way. But it's clear that I can pick W1 to be A times B and W2 to be C times A times D. And so there is always a way to break W as the product of two things. Yeah, I hope that's clear. Okay, so that was my aside, which I'm probably going to rub out now. Okay, so back to the proof. So we've written W as the product of two elements, which are themselves products of axes. And what do I want to consider? I want to consider V times W. Well, I can write V times W as V times W1 times W2. And now I can use the properties I'm Frobenius and move one of these across here. So let's have V times W1 times W2. Now I'm also, my algebra is symmetric. So it doesn't matter if I've got V times W1 or W1 times V, they're the same thing. So I can move the V over to this side. So that is W1 with V times W2. So if you like in here, there is me swapping these round, but that's not necessary. And now again here, I really want just V on this side, so I can do the same trick again and move W2 over and get W1, W2 with V. And now just remember that that is W with V, and hence I've shown that V comma W is equal to W comma V. That's the end of the proof here. Okay, so necessarily all my Frobenius forms are symmetric, so that's quite nice. What other properties do they have? Well, they behave nicely with respect to the decomposition that you get from an axis. So how do we see that? And what do I mean precisely by that? So for an axis A and X, say, I get a decomposition as the eigenspaces with respect to A. And this decomposition is orthogonal with respect to the Frobenius form. So specifically, what do I mean? i.e., a lambda of A is perpendicular in the form. So actually, okay, I'll write it like that, and then I'll write what it means. So this is going to be a lambda of A, comma, a mu of A is 0 whenever, if lambda does not equal mu. So different parts, different eigenspaces here are orthogonal. So again, how do we see this? Well, let's take two eigenvectors then. So let U be in a lambda and V be in a mu with respect to A. Then, well, what do we know about lambda, about U? U is a lambda eigenvector. So I can write U, if I multiply U by A, this is going to give me lambda times U times V, because A times U is just lambda U. On the other hand, I can move this A across my product here and get A times V. And playing the same trick here, I get mu here because it's a mu eigenvector. But now I have that UV, and I have UV here, and so I must have, so this implies that either lambda equals mu or UV is 0. Oh, my thing seems to be lagging behind slightly. Okay, and we've assumed that they're in different eigenspaces. In here, I've said if they're not equal, then we must have this. Okay, so that's a couple of nice properties of my Frobenius form. So you can already maybe see why it might be a useful thing to have around. Let's just think about now certain values in our Frobenius form and how you might, or what are necessary conditions for defining them anyway. So recall that for any axis, I've got this decomposition here. So I can decompose some elements in my axial algebra, U say, with respect to this decomposition. So for U in A, I can decompose U with respect to A to get U being equal to some sum of U lambdas, where U lambda lies in the lambda eigenspace with respect to A. And so I can consider these U lambdas. So I'm going to call, we call U lambda the projection. Oh, my writing's terrible today. The projection of U onto A lambda. And one of these projections is particularly nice. So if we have a primitive axial algebra, so that's one, remember, where the one eigenspace is just one dimensional, then this projection, U1, is just going to be some scalar multiple of the axis. Okay, I don't quite have room at the bottom of here. Let me go on to the next page. So for a primitive axial algebra, so remember that this is where A1 is just spanned by A. So U1 must equal some scalar amount of A, where this thing is some scalar. And this thing here, so I've written it like this. So phi A is linear in U. That's easy to see. If I have the sum of two things here, then the sum of their projections to the first component must be just a sum of the two individual projections. And so that means that this here is going to be a linear function. So this is a linear homomorphism here. Or linear function. Okay, and how does this help us with the Frobenius form? So a proposition so I should, let me just state precisely here, let this be a Frobenius form. I'm shortening things now. On a primitive axial algebra, then what do we have? Well, the first thing here is that if I take some axis and some other element u, then the value of this is exactly this projection which I've just defined times by the value on the axis. My second point here is that this is uniquely defined by the values on the axes. So if you wanted to define a Frobenius form, you just need to define it on the axes, and then you need to check that it really does define a Frobenius form. But this should define it for the whole of the rest of the algebra. But it's still very much non-trivial to check for the remaining, for the rest of the algebra. And finally, the third part, all the time I've wanted things to be invariant under the Miyamoto group. So what about this? So this is invariant under the Miyamoto group. if and only if A if and only if the values, if and only if when you apply an element of the Miyamoto group to the axes, then you have this for all A and X. Okay, so let me go about proving some of these. So for the first one, well, you might have guessed this already because I had this nice lemma earlier about the decomposition being orthogonal, and now I'm talking about one particular one here. So in particular, let's just think about this a minute. A, with respect to A, only has a 1 component, obviously. All the other parts are, all the other eigenspaces for A with respect to A are empty. U, well, then our lemma before said that A must therefore be perpendicular to all of its lambda eigenspaces for lambda not equal to 1. So this can only depend on the projection, and then this follows immediately. So let me write this out. So by our previous lemma, A with a lambda of A is 0 for all lambda not equal to 1. So this implies that A with U is the same as A with the projection onto the first component. But as we saw earlier, this is just this value times A, and then I bring that out the front. To get that. Okay, well, that was straightforward. Let me just give you maybe a sketch or an idea about 2. So what was the second one? The second one was that this is uniquely defined by the values on the axes. So the way I want to prove this is by proceeding by induction on, so again, my axial algebra is spanned by products of axes. So if I can show that every product is uniquely defined by products of axes, by just the values on axes, then I'm done. And the way I'm going to do this is by induction on the length of a product. So this is proved by induction on the length of a product of axes. And as you imagine, the start case, the base case for my induction is products of length 1. Well, those are exactly axes. So obviously the value of the axes is determined by the value of the axes. And so we just need to look at longer products. And again, we're going to use exactly the same trick here. So, actually, the base case is slightly different to this. So proof by induction on the length of a product of axes W. So we only want to do 1. So if the length of W is 1, it implies it's an axis, and by by part one of this, we have that W comma V is equal to the projection of V onto W times W is the axis times W, because it's an axis. And if the length is greater than 1, then I'm going to write W as W1 times W2 again. And my inductive step is going to be the following. So I want to know what this value is. So in particular here, this is determined by the value on the axis. And here, in this case, now I don't have axes, but I know that my W, I can write it as a product of axes. And now I can move this over to the other side. And now this is a product whose length is strictly smaller than W here. Okay, I took the so W1 and W2 cannot be the identity if we have an identity in our algebra. They have to have length at least 1 or more. And so here W1 is strictly smaller length. So W1 has strictly smaller length. Now, this is where this is my inductive step. So use the inductive hypothesis here, and this completes the proof for 2. And I think I'll leave the third one as an exercise to you. It's just a bit of playing around with applying group elements and so on. Okay, so let me make maybe a couple of remarks here. So the first is that you've seen a couple of times that this way of doing sort of inductive proofs on the length of things, length of products here, where I split them in 2, there may, of course, be several different ways to write W as a product of different axes. And then there may be, so each one of those may have a different splitting. But because the value of the form is set, it doesn't matter which one of those I pick. And what else do I want to say? Okay, so also part 1 here, suppose U is an axis, then I have, say, U is some axis B. Then I have A comma B is the projection of B onto A of AA, but I could have also done it the other way around and had the projection onto B of A of BB. And so the value AA is linked to the value of BB. So it's not true that you get completely free rein over picking the values on every axis, because the value on some axes may determine the value on other axes. In particular, if your form is invariant under the Miyamoto group, if I pick one value here, then I get the value on all of its orbits must be fixed. What else do I want to say? In many previous papers, you might see that the value AA might be fixed to be 1. I don't make that assumption here, because it could be possible that okay, both of these suggest that, I can't quite say this comment yet, because I haven't introduced the thing which I'm going to introduce a bit later. Yeah, let me say it later instead. I guess from now on, the only other remark I want to say, which is an important remark, is all known examples. I said this last time as well. All known examples of axial algebras admit a Frobenius form which is invariant under the Miyamoto group. There are certain classes of axial algebras where we can prove that that's true. So it's a theorem which comes from Hall, Segev, and Shpectorov, that every axial algebra of Jordan type eta admits a Frobenius form and one invariant under the Miyamoto group. So we know for this class of axial algebra, and a conjecture, this is myself and Sergei Shpectorov. So we conjecture that every axial algebra of monster type a quarter 1/32 admits a Frobenius form. So why don't we, I mean, we could maybe have made this conjecture slightly more general for general alpha and beta here. At the time when we made this conjecture, really the only examples we had were coming from the Griess algebra. So this is where we had evidence for it. But maybe we might be slightly more brave today and say that any axial algebra, any monster type alpha beta axial algebra had a Frobenius form. And I guess to finish, I've said occasionally that these Majorana algebras were predecessors of axial algebras, and you can now, I can now say a slightly backwards definition here, as it were. A Majorana algebra is an axial algebra over the real numbers of monster type m a quarter 1/32 such that it has a Frobenius form where the value is 1 on all axes, and it is positive definite and 2, Norton's equality holds. And what does that say? Well, it says if you look at the values of x squared and y squared, that should always be greater than the value of xy with xy for all x and y in your algebra. So why this, why do I say equality? This should be inequality. Why this inequality here? Well, this is something which you see hold in the Griess algebra. And originally, Majorana algebras were defined to generalize what was seen in the Griess algebra. So this seemed like a reasonable property to have, although, and similarly with the Frobenius form, all of those Frobenius forms are positive definite. They have this property here. And so axial algebras, essentially, they looked at some of the work done on Majorana algebras and noticed that this second thing here was almost never used. And you could drop this first thing here and then just generalize these two bits. So yeah, this is a rather sort of backwards looking definition. Okay, so in the time I have left, let me get started on ideals. So I guess the first thing to note is that whenever we have an algebra, it's natural to study ideals. And moreover here, it's going to be useful for us because when we do have ideals, we can quotient by them and we get new axial algebras in that way. And I guess most of the work in this section comes from a paper of Karsraw, myself, and Shpectorov. Although some was previously known for Jordan algebras, maybe. Yeah, one thing was previously known for Jordan algebras, Jordan type algebras. Okay, so remember that result that I had last time, where if I have a subspace, it's invariant under the action, or which is invariant under the action of the adjoint of an axis, then it decomposes as the direct sum of eigenspaces. So recall, if W is some subspace, which is invariant under the adjoint, then W is going to be equal to the direct sum over the eigenspaces here. So this holds for ideals. For an ideal I, we get the I we get this decomposition for I where the lambda part of I is just I intersected with a lambda. And remember that previously we had this important result, which was this corollary, which all ideals are invariant under the Miyamoto group. So that it's worth stating again because it's an important result. Okay, so I'm going to assume from now on that that A is primitive. What does this allow us to do? Well, remember those projections earlier. Well, if we're primitive, then the one part has to be one-dimensional. And so this I1, well, it can be at most one-dimensional, but it could also be zero-dimensional. So I1 is either 0 or 1 dimensional. Another way of putting this is if it's one dimensional, so I guess this is with respect to A, some axis. If it's one dimensional, then I must contain A. If it's zero dimensional, then I does not contain A. Yeah. So what I'm going to do is I'm going to split my ideals into two different classes. My ideals into two different classes. So the first class is ideals which contain no axes. And the second is ideals which do contain axes. Okay, so maybe, I mean, we could have made this split before, but actually it's this observation which is going to allow us to sort of do this in a useful way. So we'll really see that these two types of ideals behave in a different way. So let me consider the first type of ideal. So we consider ideals I which do not contain any axes. Okay, well, let's have our first result here. So let Y be some subset of axes of, they're necessarily primitive. I'm only considering primitive axes here. Then there exists a unique largest ideal which contains Y. Okay, so how do we go about proving this? So, sorry, I think I can hear somebody asking a question, but they're very quiet. I'm so sorry, I just can't really hear well. Could you maybe write it in the chat? How do I get to see the chat here?
Ну, там два таких больших датчика к животу ставят, и там слушаешь. Ну, как, в принципе, само оно выглядит как кардиограмма, так как кривулька. Наверное, действительно как кардиограмма ребенка.
Ah, I think that might be in Russian, so maybe I'll carry on for the minute, and if anything comes up in the chat, then I can answer it.
Но тут вроде на больших сроках исследования только делают так. Вот.
Right, so in the proof here, I have an ideal here. Right, so how's the proof go? So an ideal which doesn't contain an axis, this is the same thing we said before as the one part of my ideal being just the zero subspace. In other words, it's the case that my ideal must be contained in the all of the subspaces which aren't the one subspace. And so my ideal contains no axes so I contains no axes if and only if I is contained in the intersection over all axes A and okay, so now let's consider the sum of any two ideals which lie in this intersection. Well, clearly their sum also lies in this intersection, and so there is a unique largest one. Since the sum of any two ideals or any two such ideals also lies in the intersection, there is a unique largest such ideal. And that's exactly what we want. And so it's clear that I can now make the following definition, just squeezed on the bottom here. The radical RAX of a primitive axial algebra A is the largest ideal which does not contain running out of room, any axes from X. So this lemma makes this definition well defined. Okay, so we have this radical now. That's why my topic is the radical for this. And what can I get through reasonably in the time here? So I have a theorem here. So my definition here seems to, again, rely on a specific set of axes, and I don't want this to be the case. So my theorem here is going to be the radical is stable. So recall what that means. So maybe i.e. if I've got two equivalent sets of axes, then I need both of those to be primitive, of course. Then the radicals with respect to either must be equal. Okay, maybe I will just do this proof. I'm going to have to skip out of one of the slightly longer proofs in a minute, maybe. How do we go about proving this? Well, what we can do is we will show that the radical equals the radical defined by the closure. And this will be enough because then if I have this, then that will be equal to the closure of y if they are equivalent. And if I've shown this for all axes, then I'm done. Primitive axes. Okay. And how do I contain this? How do I define this? Well, this contains no axes from this x bar. So in particular, it also doesn't contain any axes from x. So in particular, it contains no axes from x. And this implies that this must be contained in the radical the ideal which contains no axes from x. Okay, so we just need the other containment, and we use this result, I guess, on the other hand, ideals are invariant under the Miyamoto group So if an ideal is invariant under the Miyamoto group, then R A of x, this by definition contains no ideals from x. So this contains no ideals from x, but it's invariant under the Miyamoto group, so I can act on x by the Miyamoto group. And from a previous lemma in that, when we were talking about closed sets of axes, this is equal to that, x bar, and so we have the opposite containment. And this completes our proof. Okay, so let me get to at least stating the main theorem in this section. So I said before...
Excuse me?
Yes?
On the last slide, did you mean to write contains no axes or no ideals?
Ah, yes, thank you very much. It should say contains no axes. Yes, thank you. Yeah, the argument is that by definition, this doesn't contain any axes from x, and it's invariant under the Miyamoto group. So I act on this by the Miyamoto group, and I just get the ideal, and I act on x by the Miyamoto group, and I get x to the Miyamoto group, which is x bar. Thank you. Okay, so earlier in this lecture, I was talking to you about the Frobenius form, and I said that it would be useful, and it's going to be useful for us here. So a priori, if I said, calculate for me the radical of your favorite axial algebra, you would probably have a hard time because you'd have to try and think up some ideal. Well, it can't contain any axes. So you multiply together some elements which aren't axes, but they might end up, their products might end up containing axes. Oh, well, that's now not in the radical and so on. So it's difficult to do that. But the Frobenius form is going to make this much easier for us. So let's just recall that for any bilinear form, the radical of the bilinear form is defined as follows. I'm going to write A perp. I'm assuming my form is on A. A perp, this is the set of V such that V is perpendicular to, maybe I'll write that as X. V is perpendicular to X for all X in A. And actually, this is a subspace. So it's not just a set, it's a subspace. So a lemma is that the radical A perp of a Frobenius form is an ideal of A. I am going to, given that I want to actually state a theorem here, which I'll prove next time, this proof is going to be an exercise for you. And guess what? I might have introduced potentially confusing notation with two different radicals, but the main theorem in this section is the following. And it says that if A is a primitive axial algebra with a Frobenius form, then the radical of my algebra is equal to the radical of my form if and only if I have that the value on axes is non-zero for all of my axes. So I'm going to prove this next time. This is an important result. Let me just say quickly why it is important. It's important because it allows us to easily calculate what the radical is. So if I've got a bilinear form, it's just a linear algebra exercise to calculate what the radical is. So I can look at for instance, the gram matrix of my form and look at the null space for that. So look at the determinant, find out if it has a radical or not, and if it does, find out what the null space there is. And that is exactly the radical. So it's a linear algebra exercise. It's easy to calculate. And that allows me, again, this is easy to check. And by the way, all forms, I said before that all axial algebras we know admit a Frobenius form. They all admit one which are non-zero on the axes. And so this allows us to easily calculate what the radical is. So it allows us to get our hands on what this, one of these classes of ideals. Okay, so I'm going to go through the rest of this and talk about the other class of ideals next time. and also give an idea as to some research avenues in this area, some unanswered questions and so on. Thank you very much.
Thank you, Justin. If anybody has any question or comment.
Yes, I would like to ask a question, please.
Sure.
So earlier we talked about this theorem. The radical is stable if that is, if x is equivalent to y, then the radical of given by x is equal to the radical equal to y. And then you mentioned that given we take this given that y is also a primitive set of axes.
Yes.
So what does this equivalent relation preserve? Does it give us a clue that this y might be already primitive by this equivalent relation and maybe some other extra condition, or it does give no clue on that?
That's a good question. I don't think it gives an idea if it's going to be primitive or not. I see no good reason why y would have to be primitive. Yeah, that's an interesting question. It's well worth thinking about, actually.
So you came across also examples of a set of primitive axes which is equivalent to a set of non-primitive.
Well, let me have a think. I can't quite think of one off the top of my head, but I think I could cook you up an example, yeah, because the kind of thing I'm thinking about is if I have, in some of the small examples, there's also an identity element. And there, 1 minus an axis, if you took a 0, so you do 1 minus axis, and if you multiply this by something which is in the 0 eigenspace with respect to A, you would get 1 times x minus a times x. That would disappear. Then you just get left with x. So this would be in the 1 eigenspace for this, but this, by the way, is also a
idempotent.
An idempotent, exactly. So this here is in the 1 eigenspace for this idempotent. And so there's, if your 0 eigenspace, where we chose here this in the 0 eigenspace for A, I think I could cook up an example where the 0 eigenspace is bigger than 1 dimension. And so therefore the 1 eigenspace for A would be bigger than 1 dimension, i.e. these aren't primitive.
Yes.
But the algebra is still going to be generated by the set of all 1 minus A's.
Yes, thank you very much.
So I think I can cook up an example like that, but I don't quite have one to mind off the top of my head.
Yeah, but Yeah, it gives me the idea. Thank you very much.
Right. Yeah, good. Thank you. It's a good question.
Any more questions? Okay, if not, let's thank Justin again. And see you on the lectures in the afternoon.
Thank you very much.